All right, so good morning and welcome to everybody to our number 12 cultural seminar in the Index Fresh avocado series. I'm Giovanni Cavaletto and just want to say welcome and thank you all for coming. Today we are going to be talking about fertilization, irrigation, and salinity. We have two excellent speakers from the University of California. We have Dr. Dave Crowley, who we can all welcome back. I think a lot of you recognize him from one of our previous seminars a couple of years ago. And we also have Dr. Peggy Mauk, also from the University of California down at Riverside. So without further ado, welcome to Dr. Crowley.
All right, thank you, Giovanni. It's a real pleasure to be back here again after, I think, 3 years ago. I gave a talk then on fertilization of avocado. And today we're going to be expanding that topic to look into salinity and irrigation practices, which I know are really big, important topics for all of you. Now, I've been working on avocado for probably about the last 20 years. I worked for quite a while in zinc nutrition and iron nutrition. And back in about 1996, I believe, I started work on salinity. And at that time, we were looking at different rootstocks. And there's a lot of great work that can be done yet on rootstocks. It's taking place in our rootstock breeding program, also the sign selections. And one of the first things when we start talking about nutrition and irrigation is to keep in mind that the combination of the scion and the rootstock is extremely important because you're going to have different responses depending on the type of rootstock that you're working with. And so this leads very closely into the topic that Peggy Mauk will be talking about with the rootstock selections that we're working with now, looking for improved salinity tolerance. So what I'm going to be talking about primarily during the first part of my talk is the soil-water relations. I think this will be very important for you because irrigation is one of the most important considerations when you're looking at the difference between profitability and not. Also, there are a lot of nutritional problems that are associated with irrigation management, so they couple very much together. It's a very holistic problem when you look at how to manage avocado to obtain the best possible yields. And then also we have the difficulty, the challenge today in obtaining a consistent water supply, and there's a lot of interest moving towards use of recycled water. And I've been working with several groups, including the Escondido group, to look at the use of recycled water for avocado production. And there we're looking at water that's generally higher in salinity, a little bit higher levels of boron, and definitely higher levels of chloride. So as we start looking at this as a potential water source, we really need to look at how to precision manage our orchards in order to bring these up to the highest possible production levels and increase their tolerance to salinity. Now in California today, everybody here is very well aware that we're in the middle of a drought, a very prolonged drought, and that this could continue for some time. We're looking at use of groundwater resources, and many people have looked at their well water as a potential water source. And even now, we're just starting to look at the regulation of well drilling and quality monitoring of our wells. Agriculture in California today is using 80% of the water supply, and there's a lot of pressure on it now with cutbacks in some districts of 25–30%, and without the rainfall, then we're really on the edge. But this is a diagram from California agriculture, and they're looking at the potential water savings from improved irrigation scheduling, irrigation technology, and even the use of regulated deficit irrigation as one way to save potentially 30–40% of our water supply that we have. So the best source of new water that we have is actually by more efficient use of our water. And then when we start looking at recycled water and bringing this in, then it is possible that in the future we can have some consistent supplies for agriculture. But as shown on this slide, you can look at the number of million acre feet that are potentially saved by these different types of technologies. And this includes The regulated deficit irrigation, this is the top part, this could potentially save about 1 million acre-feet a year in California. We see down here the blue, this is efficient irrigation technology. And then actually the biggest gain to be had is through efficient irrigation scheduling. And this is interesting because in our project we're looking at different groves to figure out the different elements that contribute to yields. We have some growers that have watered 3 times a day. That's their irrigation schedule. Believe it or not, yes, 3 times a day, and it can be done. Creates problems, but it can be done for a while. We have other growers that get their water every 3 weeks, whether they want it or not. And of course, at that point, most of the trees are pretty well dried out. Sometimes water is delivered on a strict schedule. Other times you have options about when you're going to apply it. But clearly, improved irrigation scheduling, getting the water on at the right frequency and duration is one of the biggest areas that we can improve. Now, the other aspect is while we're working with water, we need to consider the water quality very carefully. And avocado, of course, being one of the most sensitive plants to salinity, along with strawberry, actually determines the water quality from discharge from the wastewater treatment plants, where we are setting limits at 100 parts per million of chloride based on avocado's tolerance. And probably it should be a little bit lower, more like 80 parts per million. But also we have to consider the total dissolved salts, the total salinity, and this is measured in terms of parts per million. How many milligrams per liter do you have of the total salts? And then this can be converted over to a value of EC. I tend to prefer the EC units, 1 to 4. It's very simple. But an EC of 1 is equal to approximately 650 parts per million of salt. Meaning that in a bottle of water that you have approximately about a half gram of salt in that bottle of water, if it's a normal, good quality drinking water. So ECs of 1 are generally, and less, are generally pretty good. As you start going above 1 for avocado, you're going to start having problems. Generally about 2, this would be unuseful. You can have this as a water source for certain rootstocks, because I know that we've used this before on certain rootstocks, but for most of the industry where we're growing Mexican rootstocks, this would be unsatisfactory. Now, how much salt does that mean when that you're applying when you're irrigating? We often forget about this salt that is in the water that you're importing into your orchard. And I think I talked about this before when I was here, about the total amounts of salt that you bring into the orchard are some 2,000 kilograms of dissolved salt every single year. If you're applying 4 acre-feet, that's like bringing in several pickup truckloads and distributing it across your orchard. Now, of the total dissolved salt, that's about 1,000 kilograms of sodium chloride. So that's, again, taking about 1,000 boxes of Morton salt and coming in and putting about 10 on each tree. If I did that, you would probably throw me out, and with good reason. But this is what we have to do as a grower when you're irrigating. You're bringing salt into the orchard. So a lot of what we do has to be with salt management, pushing these salts down below the root zone and keeping them out of the way where they can be not taken up by the plant. The symptoms of salinity intolerance in avocado include all sorts of physiological responses, poor root growth, reduced photosynthesis. We see leaf burn symptoms. The most striking thing that everybody is familiar with is this problem with the leaf burn, where the tips start out with a severe burn, and then you see the burn coming along the edges, and eventually it can cause a complete desiccation of the leaf and defoliation even. But well before this happens, even before you see the first symptom of salt damage to the leaves, you will already have reduced root growth. And if you have reduced root growth, that means you have less contact with the soil to take up water and nutrients. So your water and nutrient use efficiency begins to go down already before you have this problem that appears in the foliage. The challenge of salt is primarily related to chloride. We have some problems with sodium in certain areas, but this is, in my experience, in the trees that we've been looking at for years, we're not really seeing a problem with sodium damage associated with the leaf burn. But they do have similar types of patterns, except that the sodium appears primarily as this mottled spots in the middle of the leaves, where the chloride damage is associated primarily with the tips and the edges. And that's because it's taken up and moved through the veins and it ends up in these outer compartments. And you can actually load up the leaf with quite high levels of chloride. If you maintain adequate water supply, they'll be fine. But as soon as you go into an event where they're drying out and the leaves suffer a little bit of water stress, then the salts are concentrating in the leaves. They lose their succulents. The salt concentrations are actually increasing in the leaves as the water goes out. And then you get this burn and defoliation. So what levels of salt can we use, and what is the sensitivity? And these are some of the main questions that we started addressing years ago. But the literature is fairly incomplete on this. In fact, our best reference that we have is from Oster and Arpaio's work. Back in 2007, they completed a study and then published this work where they looked at a yield function, or they developed a yield function model for avocado. And this was based on Mexican rootstocks, one situation, and we have to have some room for error here because it is just describing one situation. But according to their findings, what we see is that we have a threshold that occurs at an EC of about 1. And then after that point, the loss in yield declines at a linear rate until you go up to EC of 2, and at this point, you're down to about 10% of your potential yield. So this would be completely devastating. We know in other cases, though, with other rootstock and scion combinations, that you can get by with different levels of water quality. So one of the things that we're concerned with is how much does this really apply to all the different rootstocks and combinations and soil types as well. So this needs to be much better refined. And that was the main principal goal of our research. There are different effects of salt. I mentioned the sodium chloride and the chloride damage to the leaves. But the total EC is primarily affecting the water uptake by the plant. We have to separate out salinity into two different components. This is really important because the first component is the effect on water uptake. And we often think about transpiration, water being sucked out of the leaves and moving into the atmosphere, and then this extending all the way down to the roots. But the actual entry of water into the plant is through osmosis, and that requires energy. And that means that you have to have a warm soil temperature, you have to have oxygen present. And then you have ATP, which is generated. This is the energy currency. And it's driving these pumps, setting up a membrane potential here that drives in these nutrients. And the salts are accumulated against a gradient, going from low to high inside the plant. The water then follows into the plant, into the roots. And once it gets past the outer compartment, it then enters the transpiration stream, and that's where transpiration takes over. Under high salt conditions in the soil, we have the opposite occurring, where the salt is so much higher outside the plant root that the water is actually leaving the plant. So this is very much analogous to trying to drink ocean water and survive. It would actually take the water out of your body if you consumed ocean water, because the osmosis would go in the other direction. So one of the first things that we need for water uptake and nutrient uptake is to maintain a well-aerated root system, and also you can have effects of soil temperature on this process as well. And then, of course, trying to keep the total salts down. In our experience, looking at lysimeters, which collect water from the root zone, from the soil, we find that it's very seldom that you will have an EC of the soil solution that goes below or goes above an EC of 4. And at this point, this is probably about the level where avocado is able to extract water. But once your soil EC goes above 4, it's going to be very, very difficult for it to obtain more water. And as that EC is going up, correspondingly, you're going to have less water entering into the plant. So maintaining the EC at a low level is very important. Typically, the EC of the irrigation water is about 1/2 of that which occurs or that you would measure in a soil saturated paste extract. So if you're irrigating with an EC of 1, typically your EC of your soil would be about 2 in a saturated paste extract. And at that point, if you're at an EC of 2, probably you're already looking at having to do some leaching to keep the salts from accumulating. All right, well, given all this background on the importance of salinity, of irrigation scheduling, and so on, it was of interest to do a survey to find out just what practices growers are using for irrigation monitoring and for scheduling. And everybody that's in business, if you're growing avocados and you're getting a profit, you're probably doing a pretty good job already with your irrigation scheduling. But it doesn't mean that you couldn't greatly increase your profitability by improving the water use efficiency. Any water that leaves that root zone, you want to ideally keep the water right where the roots are. And any water that goes below that root zone is a hole in your pocket. That's water that the trees won't access. Now, we need a small amount of that just to move things down through leaching. But if you're consistently overwatering, then that's going to be a water loss, profit loss. And when you're looking at 700 to 1,000 or more for an acre foot of water, 4 acre feet to an avocado tree, that's a big baseline for your profits before you start making money. Well, in our survey, this was conducted by my graduate student, Julie Escalera, and she had 130 responses that came back and is now writing up the final analysis. But some of the questions that she asked the growers were, how often do you measure your soil for total salinity? Do you take a soil sample and make an extract? And in this case, we found that approximately half the growers do not keep any measure or ever measure their soil salinity levels. It may come in on a report, but in terms of looking at what's going on in the grove and walking around and checking out the salinity levels, never. Others, 32% would do this annually, and almost no one is doing this on a regular basis. 3 that would do this on a monthly basis. On leaf nutrient analysis, this seems to be well accepted by the industry. Some 70% of growers annually test their avocado trees for nutrient levels, and 14% never. But on these other questions here, how often do you test your irrigation water for salinity, even knowing what's coming into the grove and what you're applying? Again, 42% never, they don't know what's coming into their soils with their irrigation water. 34% do this annually. And then how often do you measure the soil water status to determine, is it really wet? Now, most growers, and this is a good technique, will use a probe or a shovel, and you turn over the soil and you feel it, and you can get an idea about how wet the soil is. It's pretty good. But when we start looking at the details on optimizing water, you're going to see that we're talking about the differences of a couple percent, going maybe from 32 to 34% is the difference for providing the optimal levels of water to the tree. And I doubt that anybody can really tell with their fingers or a shovel these levels of soil moisture. But overall, what we find is that even using a tensiometer, some over half the growers are never looking at their soil water status. Obviously, they're doing something with scheduling, possibly using Tzimmes or other techniques, but never is a pretty blank picture for the understanding of soil-water relations. Now, there are some very inexpensive tools that you can use to look at salinity, and I've been recommending this for years. This is a Salinity Pen. There's several on the market, but this one cost about $125, and I carry one around in my backpack. It's, I think, a very useful tool for anybody working in an orchard or farming operation, because they're so simple to use. And it has 3 buttons on it. You make a soil water extract 2-to-1. You can do it with tap water, but you have to do some adjustments in your calculations. Much simpler to use distilled water. And you simply take a core, if you want to know where the salts are in your soil, and if you're effectively leaching, you take a soil core down to 18 inches, and then divide that core up into 3 fractions. Prepare a 2-to-1 soil water extract. Let it sit for about 15 minutes while the soil is settling. And then measure the EC. So you just push the button and multiply times 4. If it's greater than an EC of 0.5 in that system, then that corresponds to an EC of 2.0 in a saturated paste extract. So that would tell you then that it was probably time to at least think about leaching. And you can see where the salts are in the soil and how effectively your leaching program is working. So that's a very simple tool that already can greatly increase your productivity by developing an effective leaching and irrigation program. Now, the amount of water to apply. This is really a big question. I think you get growers together, and one of the things that they like to talk about is there's irrigation scheduling and the variability in their soil types and the different water relations that we have for these different soil types. But I wanted to go over this in some detail because this is probably the most important consideration when you're designing an irrigation scheduling program. You have to know what the soils are in your orchard and how much water that they can hold. And then how much water is remaining in the soil after you're finished. This is water that's unusable, but it's still there in the soil. So when you're looking at volumetric water content, how much water is actually in the soil, you need to have this image in your mind about what's actually available and what's unavailable to the plant. Now, the soil is 50% pore space. It's hard to believe because it's so firm and we walk on it, you'd think it would be like a carpet or a sponge or something. And actually the sponge analogy is pretty good. You can imagine different types of sponges. Some are sort of dry and others are very large pores and so on. They hold different amounts of water. As you squeeze, it takes different amounts of pressure to get that water out of the soil. But 50% of the typical soil is airspace, air-filled space when it's dry. Now, if you fill that up to saturation, then of course, just like a sponge, it's going to drain, and that will be the free water that falls out of those large pores. And at that point, ideally, we would like to have in the soil 50% pore space, of which half that pore space is water, and the other half is air, because roots need air as well. And if you decrease the water level, or decrease the airspace to less than about 15%, then it's very difficult for the trees to get enough oxygen. At that point, then they go into what's known as hypoxia, oxygen deficiency, or we call it waterlogging as well. And then they're not able to produce energy. They can't operate to produce ATP. The pumps fail. The nutrient uptake ability fails. Even water uptake fails at that point. So you can again be in a wet soil, and there's just simply not enough oxygen for the roots to function to allow water uptake to occur. Now, on this diagram, this shows sand, sandy loam, loam, different soil texture types, and it shows the amount of available water that we have. Typically in a sandy soil, you're looking at somewhere 10, 11, 12% as the total at field capacity when it's freely drained. And then when you finish, you're down here at about 4 or 5%, a little bit of residual water left. On the other extreme, when we go over here to a clay soil, we have up here 45%, and this is at field capacity. Now we're in the danger zone up here because we've gone down to less than this 35% level where we need that 15% up here that's filled with air, oxygen, so that the roots can respire. And under this condition, this is when you're in danger of hypoxia. And avocado is extremely sensitive, at least the rootstocks we're working with, and some more so than others, are very, very sensitive to this hypoxia. So what we would like to do then is maintain this water at a lower level and maintain aeration through different cultural practices, preferably even avoid these heavy soils. But if you're in these soils, develop practices that will allow you to improve the aeration status of the roots. Now, along with that diagram there, which was the volumetric water content, this tells you the amount of water that's actually in the soil. We can also consider the force that's required to extract that water from the soil. And that is determined by the water potential. How tightly is it held onto the soil particles? And in order to get that last water off of a soil particle surface, it's pretty much like ice. It's held on there in a monolayer of film. and it takes drying in an oven at higher than boiling water or boiling temperatures, 212, in order to get that water to come off. So what we're looking at then is the water that can be obtained from 0 to 50 centibars. Now, if you look at the volumetric water content, this is normally when you would turn on the water at 50 centibars. At that point, we're here at about 5% on the sand. So this would correspond, and generally because sand, notice how this curve takes off like this. Normally, you would begin thinking about irrigating at about 25 because there's very, very little difference in the amount of water. The volumetric water content decrease here going from 25 to 50 is minuscule. So generally 25 is set as the safety level because there's just not a lot of water to be had in the sandy soil. On the other side, a clay soil at field capacity is going to be here somewhere around 40%. And then as it drains down, going to 50 centibars, again with this same type of curve, then we have a little bit higher water availability, so we can set it here at about 50 centibars with relative safety. And at this point, we're looking at about 25% water remaining in the soil. So we need to measure two things, both the water potential and the volumetric water content in order to have a full picture of what's happening in the soil. Now, this is much more challenging than anybody would think unless you're an avocado grower and have already tried to do this. I've been working with tensiometers and gypsum blocks and all kinds of equipment for a long time. And this last year, I took a dozen tensiometers home, put them in my backyard around different trees, and wanted to see just how difficult it was to deal with an irrometer. And it's actually kind of a pain in the neck. It's hard to see the things sometimes. They get kicked. As they dry out, they lose contact with the soil surface. You end up having slow response times when you water. You'll see that it takes a while for the tensiometer to come back and tell you that it would be time to turn the water off. In fact, you really can't use it for that purpose. And also then they need maintenance. The seals need to be good, and you need to refill these things. So there's a lot of, they're tremendous tools, but they're also challenging to work with. And when you spread that out across an orchard where you have many different soil types, it takes a lot of managing of data in order to try and work with these and optimize your soil moisture. The gypsum blocks are easier to use, and they are very responsive to a soil dry down, but just like the tensiometers, once you irrigate, they are slow to respond to tell you that you've saturated your soil. So what we're recommending at this point in terms of irrigation control, if you want to control this, put a gypsum block in your root zone. This could be 6-8 inches down towards the bottom of the root zone of the avocado. And then as that dries down to 25 to 50 centibars, then turn on the water, but use a volumetric probe to tell you when to turn the water off. When have you actually filled it up? Because they're very, very responsive. Now on the tensiometer, there are some guidelines that we should look at here. This works by having water drawn out by equilibrium with the contact with the soil surface here. So soil is releasing moisture and it's being pulled also into the ceramic cup. And as the water is being pulled out of the ceramic cup by the soil dry down, it exerts pressure or tension on this column, and then that operates a diaphragm up here, which then moves the spring. And so when you are at free water, when you have standing water, saturated soil, you're going to be at a water potential of 0. And then we start moving, they don't have negatives on here, but we're actually moving in a negative direction. So this is minus 20 centibars, and here between minus 10, minus 20, we're actually in the field capacity range. So sand, you could take a little bit further, and then it's time to irrigate again. They're recommending irrometer about 30. With a loam soil or silty soil, you can take it up to 50, and with clay soil about 60. But as you start going up here to 80, the systems disconnect. There's actual shrinkage of the soil, and they become relatively unresponsive and unable to go up beyond 100 centibars. So you're really working in this range. Interestingly, the tree still has a long ways to go before it would actually die. In terms of the permanent wilting point for plants, it's 1,500 centibars. So this is way off scale, but because of the way the soil dry down occurs, we have to pull this in at a much earlier level at 50 centibars for avocado. These are the volumetric water probes from Decagon over here on the left, and they sell some very nice equipment overall, which we're using in our salinity monitoring work. This is a probe that uses a dielectric potential here. It sends out a radio frequency into the soil. It comes back with a different waveform, and then that waveform is analyzed and calibrated to tell you how much water, typically in an area about the size of a coffee can, that's around the probe itself. So where you place this probe is very, very important too, because you have different canopies, sizes, you have different throw distances on your sprinklers, different wetting patterns, and the critical thing on any of these installations is to find a uniform spot that represents the block that you're trying to manage. Along with the volumetric water content, we also have two little buttons here that pick up the conductivity of the soil. They're looking at the salinity level in the soil by measuring the current that flows between these two points. And then you can get an idea about the soil salinity status as well as the volumetric water content. This is their equivalent of a gypsum block. It's a little bit better constructed, but essentially the same principle. And then these can be hooked up to a data logger that will allow you to download that information every 15 minutes. And then it sends it up to a cell phone site, and you can have a near real-time reading on what your soil water status is anywhere in the world, because you can even access in some cases on your iPhone or cell phone the information about your soil water status. Now this also generates some really useful information about the relationships between salinity, watering, and irrigation scheduling. And actually some of the growers I've talked to find that this is the most important of all. They want to know how often the soil is being watered and for how long. So if they tell their water person to go turn on a valve at this time and turn it off at that time, and they want this much water, there has to be this confidence that that's actually occurred. So by having these points here, this tells not only, this tells the interval, so in this case a couple of weeks in between the interval, and then the width of this line corresponds to the minutes that the water was applied. And you can go into a table at the top of this, switch it over to a table form, and actually get the measure of minutes that the water was applied. For example, here you see a short little pattern that was adjusted there. Now looking at this in more detail, how this works with the soil, water, and salinity relations, this is a situation where the trees were watered every 3 weeks because that was when the water was delivered. And we see that the soil water at field capacity, or immediately after watering, is at 37%, and over this 3-week period, it's going down to 22%. Now, along the way, we see that the water potential is going from 0 centibars at field capacity, going down to 427. So this couldn't even be measured with a tensiometer or a gypsum block, but with the Decagon equipment, we can take it down this low. And so we see the soil drying out. And then at the same time up here, we have the salts. And the salts have accumulated up to an EC in the system of 2.9. And then when you apply the water right after this, then you have a flushing event that takes the water salinity down to 0.75. And then as the soil dries out again, the water's leaving, the salts are staying. This concentrates and it brings the soil salinity back up to 2.9. So we're going between all these cycles with every single irrigation. And then if you apply extra water for leaching and you want to see how effective that is, this type of output could tell you what you were doing with very, very high precision. Now again, it would be hard to put enough probes into an orchard to account for all the different variation. And you like to come at it from different angles. So another tool that is absolutely valuable, probably the most important tool, if you didn't have anything else, Tzimmes could guide your irrigation to a large extent, and probably many of you are already using this. If not, it's a tremendous resource because you can go here and obtain information about irrigation in general. You can learn about evapotranspiration, all the scientific background, and pretty friendly terms. And then you can find your own station. You can set up your personal account and receive the information that tells you how much evapotranspiration has occurred. And this is based on some 120 different stations. Different numbers are open at different times, typically about 80 stations that are operating at any one time. But you find your closest Tzimmes station that reflects your area, or you can install your own weather station if you're really into precision. But this would give you a good guideline. So you find your Tzimmes station, and then it's looking at how much water is transpiring from a bed of grass that's maintained at a particular height. And then the water that's used by that is then used as a baseline, and you use a crop coefficient to determine how much avocado would have used as compared to the grass. With Tzimmes, we see some real patterns that begin to emerge, and you could begin to schedule your entire orchard based on the water use patterns on replacement, based on the evapotranspiration. So typically in January, 2.5 inches required in Riverside. In July, some 7 inches. And you can look at this from one year to the next, and it may vary a little bit, but we see this overall pattern. And consensus of many studies shows that avocado requires about 4 acre-feet for maximum production. And that's whether you're in Israel or different locations. It's typically about 4 acre-feet. Some from rainfall, some from irrigation. There are certain times of the year when we believe that the crop is very sensitive to desiccation or drought. And during fruit set and early fruit development, these are months that you would not want to have deficit irrigation. If you're constructing a water budget, you would want to fill your water budget to the requirement at this point. Might be some possibilities of doing some controlled deficit irrigation out here. But these are all things that still need to be worked out to see what is the minimum water quantity and the most efficient way that you could apply it for profitability. These are still some of the things that are of concern. Now, knowing this schedule then, if you have 7 inches that are going to be provided in July, you say, well, I've got 3 irrigation events or 4 irrigation events in July. I simply divide that in 2 or 4 parts. So then if it's 8 inches, I would need 2 inches of each irrigation. And then you look at your emitters and how they're throwing this water, and you can come up with the scheduling. And this has all been converted into a scheduling calculator. You can obtain this on avocadosource.com. And here you put in your reference ET. This is what has occurred in the period of interest here that since your last watering, how much water ET demand was there, how much was lost from the system. Put in your crop coefficient. Currently, this is 0.86 for avocado. And then you look at your distribution uniformity, because most growers are watering to their driest trees. And you hopefully, this is a place here where you could have tremendous water savings. If it's at 90%, then you're using 10% more water than what you need because you're watering that driest tree to bring it up to what it needs, and the others are getting excess. If you're at 60% or 50%, you're throwing half your water away. You can also put in your leaching requirement, typically 5 or 10%, that you want to push the salts a little below that root zone. And then you can put in your acres, your trees per acre, the surface area under the canopy, how much of that area is actually covered by tree canopy, your emitter output. Push the calculate, and it will tell you how much water per tree per day and the amount of time that you need to apply that water. So extremely useful tool. And between that and Tzimmes, I think you could manage your orchard to at least a baseline scheduling level. Now, this is also here in the soil moisture targets. I've already talked about this, about how far you want to draw the soil water down. Typically, we're looking at 75% of your water that you'd like to deplete before you would then rewater. But if you're working up in this range, chances are you're applying the water too often and are not using it efficiently. Now, avocado, everybody knows that it has shallow roots, and this is interesting. This is from a slide or from a picture taken in Peru, from an operation there where they're growing avocado in 98% sand. You think sand, this should be easy, right? Roots should just be able to grow right through the sand. We always call soils heavy if they have clay. Well, the real weight of the soil is called the bulk density. And you can start out at a bulk density of 0. That would be roots growing through air. If you have a bulk density of 2, that's equivalent to concrete. Concrete has some air in it. Solid rock is 2.6. So sand actually has a bulk density of 1.65. And that's almost approaching concrete. And as it wets up and it compacts, it can get to be very dense. And avocado trees will not grow in a soil past 1.7. The roots just simply can't penetrate through that system. Even though there's still pores there, they can't push through. And a clay soil typically has a 1.3, so it's relatively easy for the roots to penetrate through there. So what we see in a sandy soil is that many of these roots are perching up here in the top area where they would normally be, but we also have limitations on this, and it sets up this artificial horizon where roots are dying and turning over in here, and the small amount of residual clay is moving down through the profile. And if you're irrigating every single time for, say, 8 hours, then you're pushing that water front to this particular level. And you can develop a lens or horizon in your soil, even in a sandy soil, that will perch the water up and create poor oxygen conditions, hypoxia, waterlogging conditions in a sandy soil. So people are really surprised. They say, oh, I can't have waterlogging, I have a sandy soil, it drains freely. Yes, up until it hits that pan, but then after that, it remains wet. It's also influenced by the type of irrigation emitters that you have. This work was developed with pistachio, but it pertains to any orchard crop. And it illustrates the distribution of salts that occur in soils when you're using a drip emitter system. And here you see the soil depth going down to 2 meters. Here are the emitters. And then the salt levels that are occurring here in the saturation paste extract. So these are between 0 and 2, and here you can see this would be fine, this soil right in here, for avocado. But as you go out to the fringe, you're going up to an EC of 12. Well, this is equivalent to ocean water. Nothing's going to grow in that except maybe barley. And that creates this zone, almost a flower pot type of effect, where your roots then would be constrained to this area where they're getting water that's of sufficiently low salinity that they can grow. That means in the case here, this entire tree is being supported by roots that are growing in a small area around that drip emitter, and everything else is too salty. It also illustrates that the idea is to push the salts down and keep it below the root zone. Up here is your root zone, but that we need to leach and get the salts down here and eventually push it into the aquifer. And if it's an unconfined aquifer, it should sweep out and change over. But over time, if it's a confined aquifer, then you're stuck. You're going to have salt build up here eventually until this becomes very, very high level and then starts working back up to the surface. And that's the kind of thing we see down in Australia, where they have these soils that are almost impossible to remediate. The salts just keep moving back up to the top. Now, with drip, this can work for seedlings, but with avocado, unless you have lots of drip emitters, then you're going to be creating this type of situation. With a micro sprinkler, which is what most people are using now, this is a much more uniform irrigation pattern. And here you see that we've covered the entire canopy and then some with the throw pattern of the sprinkler. And this is the optimal, and again, pushing these salts down into the lower profile.
Can I ask a question at this point?
You sure can.
Excuse me. Can we take into, are we not taking into consideration the change in the soil at the top? Since given that the majority of the feeding roots are going to be in the top 4 to 6 inches, or maybe even a little less, with the maturity of a tree, with mulching and with pruning and the developing of the leaf litter, you're you're building up a pretty nice topsoil situation. Now, where does that fit into this?
That's actually fits in as a management practice, because as that soil develops and the roots are coming up under that layer, that's a well aerated zone. So you want to promote that as much as you possibly can. If you're working in a heavy soil, heavy clay soil, getting a good mulch layer on there to start with, and then as that decomposes and turns into an artificial soil, the roots will move up into that, because they're going to be growing in the top 6 inches of the soil primarily. And if you have 6 inches of a mulch that's decomposed over years, that's ideal. So you're lifting them out of that heavy soil. The other thing you can do is, if you're in a heavy soil and you have water that's being perched, you can go in with a post hole digger and punch through some of these horizons and fill those up with a compost. And that allows the water to drain down. So there's different things there. But bringing those roots up is, in my opinion, a very important management strategy. We also have to take into account the variability that occurs in soils. And at agricultural operations, you'll see in Peggy's slides the field that this represents, but it looks very, very uniform. And overall, fairly uniform in properties. But we go to the Soil Web Survey, which is another very important site for you. This gives us a map of what the soils look like on their different characteristics. In this case, the water supply from 0 to 100 centimeters. And mapping that soil, you can see that there are differences in the amount of water that these soils are holding. Now this website, I'll take you to the page here. This is the opening page, so Web Soil Survey. If you just type that in, Web Soil, as soon as you get there, you'll get to the Web Soil Survey. You start this, then there's an address button at the top. You put in your address of your orchard. Then you'll have a series of keys up here that allow you to draw an area of interest. I don't have that up here. Here's an area of interest, and you make the polygon or square around your area. And then on the side, there's a whole list of a menu of things that you can call up. And you can look at the soil texture, you can look at its hydraulic conductivity, calcium carbonate content, everything you can imagine. Suitability for construction. There's just probably at least a dozen factors that would be of interest to you as a grower. All this was done, you wonder, when did these guys come and map your soils? It was back in the 50s and 60s. And it's now resuming again. A lot of that earlier information has now been put on the website, and the USDA is going across the entire country updating this, trying to make it useful for everybody. And they went through and they dug soil pits and trenches, and then came up with these different patterns. Now, you probably have microsite variation that you would have to manage at some level, with closer inspection, but you can begin to see the different patterns here that they were able to pick up. For example, this is how fast the water goes into the soil, and over here we have 0.8 inches per hour. Then we transition to 1.7, and just a few feet away, from this side of the room to the other, it goes in at 4 inches an hour. Now that tells us that this is a potential hotspot, because if it's up at field capacity and it's not draining, then this is an area where you could have hypoxia occurring. So you'd like to know, where are these problem areas in your orchard? And this is one of the first ways to approach that is through the Web Soil Survey. Probably a more futuristic and one approach that's coming online is going to be the use of aerial imaging and looking at the water stress actually in the trees themselves to look where the variation in soil type occurs. But certainly you would want to know this variation ideally before you set up your irrigation blocks, because you do not want to cross different soil types. And also you would like to have uniform watering conditions within an irrigation block, so you avoid having wet and dry spots in the same irrigation zone. There are some indications, though, that many trees could be overwatered, and there's different situations where this occurs. One of the common ones is with the replanting of dead trees in an orchard, where young trees are put into an orchard that's mature, and then they're kept on the same emitter. And what happens in that situation is you'll end up with leaves burning, showing signs of salt burn, chlorosis, and just general poor performance of the tree because of this waterlogging effect. It's also curious that we see this increase in salinity, and I want to make a point of this because I think one of the main problems, this is a real take-home point, one of the main problems that is overwatering and driving the chloride up into the foliage, up into the canopy through these overwatering events. It's through incorrect soil moisture maintenance, we're actually creating problems with chloride uptake. Now, years ago, in 1949, researcher Haas, this is not the same person that developed the Haas avocado, but it was a researcher at Riverside, had already recognized that soil moisture was critical, and that this prolonged retardation in the movement of soil moisture through the soil resulted in problems with introduction of air and oxygen and excessive wet spots. And they were recommending at that time avoid heavy soil. So almost 70 years ago, this was a well-established fact. And we know that this is also associated with some appearance of salinity burn symptoms, which is sort of odd. Now, this could be from a couple of reasons. One could be that the soil is slow to drain, but as I mentioned, it's also this upper elevated water table. And this illustrates an effect, for example, where you have a soil that is a sand over a clay or a silt. And as you go from one texture to another in your soil profile, this will actually build up a pressure head before it can enter into this next level of profile. So in this experiment, this was at Indiana, illustration, they have to fill the soil with water until it goes out to the side and it begins to pond and it comes up to create a pressure head, and then finally it can break through to go into the next soil horizon. So if you have sand over silt, knowing your soil profile, that can be very instructive in telling you potential problem areas with this perched water occurring. So even in a sandy soil, you can have this problem with hypoxia. Now, the effects of hypoxia on leaf chloride are not yet known in avocado. We've just completed an experiment. Janessa, a graduate student in my lab, has done this, and she found very similar results, but we're going to reproduce that study before we'll release the data. But this is, I think you'll find this very interesting. These are different plants. This is saltbush, casuarina, eucalyptus, tomato, tobacco, wheat, and grape. And in this study, half the plants are maintained under aerated conditions, half are then subjected to a waterlogging event of different duration. And here in grape or wheat, this single event takes the chloride levels from 0.59 up to 0.91. So we're seeing 200, 300% increases in chloride after the plants have been subjected to waterlogging. Now, that's a huge increase. And I've been trying to dig into the literature to find out what is the explanation for this. And there's a lot of things going on with calcium and chloride pumps and so on. But the main thing that appears is that in the roots, the plants take up chloride, and it's toxic to the metabolism. So they store it inside the vacuole. It's a membrane bag inside each root cell. And they have little ATP pumps there, and they're constantly working keeping this chloride inside the vacuole. You cut off the oxygen, those pumps fail, the chloride comes out of the vacuole, enters transpiration stream, and goes up to the top. And so anytime you go through a waterlogging event, you're actually pulsing chloride up to the top of the plant. And that's occurring for all these different plant species. It seems to be a universal response in plants. And again, our recent data with avocado is supporting this, that this is also the case. Well, what's that mean? It means that actually the leaching practices are potentially the most dangerous time in terms of driving chloride up into the plant, because this is occasion when you're going to have the lowest amount of oxygen available, and if you have a poorly drained soil that's already loaded with salt, you can end up with a really drastic situation. This was from this past summer in one of the study areas that we're looking at, and it had been watered all year with chloride, water containing chloride at about 130 parts per million over the top. The grower decided to bring in fresh water and then applied this to the trees, and they watered too much. And these are DUSA. DUSA is very, very sensitive to waterlogging. And all the chloride went up into the leaves, and then they were such at a high level this went into this flash burn and defoliated. And now he's got bare fruit hanging on bare trees, and it's lost probably 100 trees from his production this year. And it's going to be dealing with trying to bring these out of this status for the next couple of years unless he just completely replants. So this is potentially a real concern, this flash burn problem. And I've heard not just this system, but many instances. Yesterday I heard another grower tell me he had the same problem with Dusa in a waterlogged soil where it went through this flash burn symptom. So let's take a look at some of the nutrient analysis work. And this is from Fruit Growers Lab. And they have been very, very supportive in our research, tremendous support for our project, providing leaf nutrient analysis for some 400 trees that we're looking at across all of the production region in California. And what we're trying to do with this is then look at the relationships between these different elements in the plant and the effects of management techniques and irrigation water, salinity, so on, soil type, on chloride uptake. Now, one of the things that you'll notice, let's take a look here. For most of these elements, this is one tree, same soil, same irrigation water, year after year. And we find, going back here, okay, nitrogen goes up and down. We know this has to be managed. It's very dynamic. But most of these elements are fairly locked in, like phosphorus. We see 0.15, 0.157, 0.156. And same thing here with sodium. You can see 0.007 all the way across. Here's 2012 where it comes up to 0.012. So it's gone up in that year. But look at the chloride. 0.4, next year it's 0.2. Then it goes to 0.27, then 0.45, and then 0.742. Same soil, same plant, same irrigation water. Why are we getting this chloride variation? Now, the only thing that could really explain that would be differences in water saturation. Because if the canopy drops, you might change the way that the water distribution patterns are occurring. It could be differences in scheduling. Something happened here that caused these hypoxic events. Now, you'll not only find it for year to year, but you can walk down the row. And we have in our design 15 trees, and you can go down 5 trees in one row and then 5 in another. As you go from one tree to the next, you'll find 0.4, 0.8, 0.2, 0.6. So all of them, all over the place. And chloride is just super variable. And so it makes it very, very difficult to explain what's going on other than some sort of microsite variation, which really comes down to the way that you apply water. Now, this is another study that's really interesting. This is a 98% sand. And I came across this in this last fall with a grower who said it was impossible for their soil to be waterlogged. And we got into a discussion about it. They had taken analyses July, August, and September, and they thought their trees were getting a little high in chloride here, going from 0.37 to 0.47. So they thought, well, let's increase the irrigation frequency. They went to a twice-a-week leaching, and then in September, it had doubled again. They had brought up their chloride levels. So now he wanted to do a leaching event to just push these salts completely out of the soil, and now he's up to 1.32. Well, we know that at 1% chloride, you're pretty much shut off all your yield. So it hardly ever gets higher than that, because once you get up to about 1%, the leaves are defoliating. So his leaching that he was trying to do actually caused this chloride pulse to go into the avocado, again supporting this theory. Another aspect of this is that iron and manganese, this is going to be a little more subtle, but iron and manganese are also more available under low oxygen conditions. They convert to a different form, and then they're more soluble and taken up by the plant. And here we see manganese acting as a surrogate for measuring these hypoxic events. And here we see 32, 66, 89, 111. So why is manganese becoming more available? And it corresponds directly to this increase in chloride. So I think the pieces of the story are starting to come together, that the chloride damage to the plant is primarily driven by our irrigation practices and leaching and overwatering. So this is the main control. Yes?
Does nitrogen application timing affect that hypoxy chloride uptake?
Nitrous?
Nitrogen applications.
Nitrogen is a very interesting part of this, this story, and I'll tell you a little bit about our results looking at nitrogen chloride interactions. Yes, this still has to be worked out. What are the best nutrient levels and how we can deal with trying to optimize the nutrition for salinity affected trees. And nitrogen is key in that. What we're looking at, your question's actually very timely, because we're looking at this whole system using what's known as a neural net approach, artificial neural networks, as a modeling tool that allows us to look at all the different factors that could potentially affect an output variable of interest: yields, alternate bearing, shelf life, fruit quality, and ultimately profitability. These techniques are being now used for handwriting recognition, voice recognition, market analysis, diagnosis of medical data, x-rays, EKGs, everything. But in agriculture, you will find very few, almost, maybe a couple dozen papers, mostly on land use classifications. So up until this point, these tools have not been applied for agriculture, but they're actually well suited, ideally suited for this. Normally in an experiment, what we try and do is we hold everything constant and then we vary one variable. And then we can see these relationships develop. But in a neural net modeling approach, what we're doing is a pattern recognition where you train the model, and I'll take you forward here just briefly to explain this, and I'm back to that. We have all these different input factors, and then it's connected through mathematical equations to a hidden layer, and then it comes out to the output function. So you start out with this data. These are real world data that you enter about your trees, and in our system we're looking at some 450 trees. And then these come in as your input, and then it looks at the output, the fruit yield. Okay, was the answer correct or not? Okay, if it's not correct, or if it's off, then it comes back and it reweights all these different linkages until it figures out what are the most important variables. And the output then tells you, it gives you a sensitivity analysis, tells you which one are controlling it. And then you can set, at that point, each of these at desired levels, and then the computer is now recognizing these patterns and coming back and giving you an actual predicted output or an association. Typically it takes about 5,000 steps, but this is, or you could have a few hundred steps depending on how simple the data are. But this is the same way that our brain works. We smell smoke, we see light, we feel heat, and go, oh, fire, we make a decision. Some things are weighted more than others. And this is also figuring out the audience. You can see, okay, male, female, how old, interest, tired. Our brains do these things, pattern recognition. And this is the basic idea behind the neural network model. Now in our study, we're working with some 12 locations that span the entire zone of the avocado production. Depending on the year, different numbers of trees in production, but about 450 trees in the entire study. Typically in any one year, only about half our trees are yielding. This is interesting. Carol Lovett finds the same thing in her data sets. So alternate bearing and just other things going on. Some trees are always low producers, others are good producers consistently. And we're working across a variety of sites that have different management techniques, slopes, soil types, rootstocks. We have 5 central locations where we have more than one rootstock, and at those we have soil water data. And then we have the other satellite locations where we're collecting the leaf nutrient analysis and the yields on individual trees, so we can tie a leaf nutrient to a particular yield. Now the idea behind this again is that if you were to control any one single variable and all the others were held constant, then you can come up with these types of relationships. For example, you could look at the pH effects. Low is good, high is bad, and there's a curvilinear relationship. You could look at salinity effects. You could look at nitrogen effects. And all these will have different effects on yield. You put them all together and you get something that looks like this. Now, how would you ever sort that out? You couldn't through a traditional statistical analysis. And that's exactly what we find when we look at avocado. You predict yield versus leaf chloride, and you get a scatter diagram that looks like this. And you say, well, there is no relationship. I could never predict chloride was causing a decrease in yield based on that data alone. Have zero relationship. these exact same data, you run them through the neural network model, and we're using, in this case, a program called Synapse. We put in all these different variables on the soil type, pH, organic matter, water quality. We look at the type of rootstock, the leaf nutrient contents, chloride levels. We can then go into different things on the output, looking at yields of primary interest. We've looked some at root mass. We can calculate water use efficiency. We can look at alternate bearing, fruit quality, lots of different variables, all based on these as input to predict the output. And doing that, this is what we find. That same diagram you just saw that was a scatter diagram converts into this. Predicted fruit yield, kilograms per tree, for the different rootstocks, Mexican, Duke 7, Dusa, and Toro Canyon. And here we see that the Dusa and the Toro Canyon are the top producers under low chloride conditions. That Dusa falls off pretty quickly at leaf chloride levels of 0.6. It would predict no yields. Toro Canyon continues to perform out here with some yields down at 0.98. So now we can get an actual numerical quantity of the effect of chloride on avocado yields. Now this is based on this model. We turned all those little slide bars. We had adjustments for each of those tools where we set it to the mean for the entire study. And across the entire, all the trees, 450 trees we looked at, the mean was 2.4% nitrogen. Phosphorus is 0.18, potassium 1.2, and calcium 1.5, et cetera. And that's what we get. What would happen if we went back in and adjusted those slide bars to maximize the yield, and then tried to see the effects of chloride again? It's the exact same plot, but in this case, we have brought the nitrogen down to 1.7%, brought the phosphorus up to 0.26%, and those are the main two switches that greatly improve the yield in the system. And here we see for these same rootstocks, even the Mexican rootstock is still producing where Toro Canyon was previously out here. Before we had complete failure above 0.8 except for Toro Canyon. But now we see by optimizing the tree's nutrition, we're able to obtain yields. And that gives us some guidelines. Are there some specific chloride recommendations that we can make, or fertilizer recommendations for trees subjected to chloride? And I think this can also be a very useful tool for looking at reoptimizing, redetermining these critical nutrient levels in the plant tissues. This was largely developed in recommendations on citrus. And so I think using these types of approaches, we can now begin to look at the relationships between these elements, the nutrient ratios, and the effects overall on yield, optimal levels. This gets back to your nitrogen question. And here we have a nitrogen interaction with chloride. And in the model, what we're looking at here is 0.1% leaf chloride on this level going up to 0.8 over here on this end. And you can see that under low leaf nitrogen, we end up dropping off in this profile. Now, as you go up in leaf nitrogen, the best yields you can see actually curve up into here, where we're getting some 600 pounds per tree. And we could even tolerate 0.4% chloride levels if we keep the leaf nitrogen somewhere between 2 to 2.4. And then after 2.4, it starts to drop off. But as you go up to 3.2, 3.4%, as long as the chloride levels are low, you'll keep some of your yields. But if the chloride levels go up to 0.8, and then you also increase the nitrogen up here to 2.8, you're in big trouble. You've lost a lot of yield. So you have a nice vegetative growth. You probably still have a lot of leaf burn because of that high chloride level, but you've really ruined your yields. So now we can start to look at these interrelationships in great detail. And again, they're associations. It's just data that has been associated, not necessarily cause and effect, but at the very least, it guides our experiments and things that we can do to try and confirm those relationships. This is for calcium and phosphorus. This one's also very interesting, again showing fruit yield here for the leaf calcium levels and the effects of chloride. And what we can see is that as you increase the leaf chloride, or leaf calcium levels up here to 2.5%, we almost completely eliminate the toxic effects of calcium, or of chloride on the system. Over here, we look at the relationship between nitrogen and phosphorus, and bringing the phosphorus levels up also are very important, and they can offset some of these detrimental effects of having high nitrogen in the plant. So these are the things that are coming out of real-world data. If you went out and looked at these trees, these are actually representing trees that are out there that have these levels of nutrients in them, and those would be their yield performances. Now, going back into the literature to try and see, well, is there a basis for these things that the model is finding? You can go back into the 90s, the 80s, and the 70s when a lot of traditional plant nutrition work was done with tanks and so on, different very detailed experiments looking at individual nutrients and their effects under precise conditions. And here we find results from one review article. This is a 1990 review. It says, nutrient additions have been more successful, such as correction of NA-induced calcium deficiency. Here, Champagnol reviews 17 publications find phosphorus added to saline soils increases crop growth in 34 of 37 plant studies. Most cases, salinity decreases the concentration of P in the plant. P additions may be required with salinity. Great. We also see here, what about calcium? As the salt concentration in the root zone increases, plant requirement for calcium increases, going back to 1970s. Another report by Moss in 1993 at the Salinity Lab, maintaining adequate calcium's important factor in controlling specific ion toxicities, sodium and chloride injury. And in citrus, calcium was found to be effective at reducing transport of chloride from the roots to the leaves. So what we're seeing is that the model is actually predicting what took decades of research to discover in horticultural plants. And that just by feeding in these data from the field, it can recognize these same patterns. So I think it's very exciting to see things that we know being confirmed and then being pointed in new directions that might help to guide our better management. This is an interesting result as well, the effects of soil pH. And this is one of the big questions. Year after year, we've been running models independently on different data sets, and we consistently find that as you lower the soil pH, that you lower the leaf chloride content. It's very hard to find a direct explanation for this in the literature. But we do know that as you bring the soil pH down to about 6.5, you increase the solubility of phosphorus greatly. You also dissolve calcium, so you're bringing in increased levels of phosphorus and calcium. It could be based on that alone. But clearly, if your pH is up here at 8, you're already setting up for high chloride with that association. And as you decrease the pH, that you can bring that down. The other aspect is sodium absorption ratio, leaf chloride content, and it tells us that the lower your sodium absorption ratio in the soil, the lower the leaf chloride content. So we're able to see these types of these things that, again, would have support in the literature. We can also go back to 1939, Hass's paper in the California yearbook, Avocado Association, at that time before it was a society. And here you can see he's grown trees at different pH levels, not even above pH 7. I don't know what pH 7, it might be below the level of the pot here. But going from 6.7 down to 4.7. In many horticultural crops, this would be associated with aluminum toxicity, but in avocado in a tropical soil, these are highly weathered soils that are often at pH 4 to 5. So it appears to be very well adapted to this lower pH. And there could just be an effective pH in maintaining a better, more vigorous growing plant that might be part of this overall improvement in chloride tolerance. But certainly based on this, our data and observations that are going on currently, it appears that lowering the pH would be a very effective management tool for improving avocado productivity.
What is your feelings, your knowledge with respect to reducing the pH with an acid addition to the water?
Very good question about what is the recommendation for adding for adjusting pH using acid to water. There's different debates on that. We were talking about that a little bit earlier about the use of sulfuric acid. And sulfuric acid is potentially dangerous if you don't know what you're doing, because you never want to add water to acid. You have to always remember to go the other way. If you have a trained person, that is the cheapest method, and it'll also clean out your lines, and it could be used very effectively. It could be directly injected. Many people are using sulfur burners, and I think this is a good way to do it. Personally, I think you feed a hopper in with sulfur. You have a $3,000 unit, fills up a tote. It costs 30, 40 cents for the sulfur that you put in there for 250 gallons of pH 2 sulfurous acid. And then that can be hauled off and injected in. So that's another option. You can use infuric. I think if you're using infuric, maybe as a way to deliver your nitrogen, that's fine, but you do not want to do pH control on infuric alone. You'll be putting way too much nitrogen on, especially if you have a calcareous soil. The soil pH will never drop below 7.2 as long as there's chalk in it, there's lime in it. All that lime has to be dissolved, and then you can drop the pH. And if you have a soil that has 3% lime in it, you're talking about tons of material that you would have to add to drop that pH. The other option is to use elemental sulfur, and that takes about 6 months or so before that reaction takes place. And what happens is the sulfur converts to sulfate, SO4, by reacting with water, and then it's generating acidity from the protons that come out. If you're adding potassium sulfate, it's already in the sulfate form. That's not going to affect the soil pH. You have to add either elemental or the sulfuric acid or the sulfurous acid. So those would be the recommendations there.
But what specifically in layman terms is happening? Let's say we use sulfuric acid. One of the problems right now, I think for all of us, at least it is for me, is the pH of available water, whether it's groundwater or from water districts and so forth, is going up and up and up. It's up as high as 7.7 for us. And so that needs to be brought down. So say if we do use the sulfuric acid, what is actually going on with the roots themselves?
You know, this is a really important question. Down in Chile, and I looked at these huge operations down there next to Jorge Schmidt's operation, one of the largest growers in the world, if not the largest. And many of the growers there are using, pumping in sulfuric acid, taking the water down to pH 2. Yeah, now I say that's impossible. You're shocking the entire microbial community, probably shocking the mycorrhizae, you know, all those effects. Then you have the effects on the organic matter and soil particle dispersion and things occurring. Yet at the end of the cycle, then they come in with a humic acid injection. And so this is being practiced. And to me, it's just amazing that you could do that and you wouldn't kill your tree. Obviously, it's readjusting quickly enough that it's coming back up, because the ideal pH is really around 6.5, possibly lower for avocado. But in terms of nutrition, 6.5 is a good pH target. I would be hesitant to do that myself on any scale, but they're maintaining healthy trees. And how they do it, I don't know.
What's actually happening to the roots themselves, or to the trees?
By having a pH shock?
Yeah.
That's a good question. Physiologically, it would probably damage some of the proteins, I would think. If you held them in that low pH, they would denature, because all these transporters, the membranes around the roots, are covered in hundreds of different proteins that are there to transport nutrients and to pick up the chemical signals and so on. But all that surface there, all those proteins are held together by different interactions that are pH dependent. So I would expect that you would denature some of your proteins and actually disrupt the function if you were going to kill the plant. But apparently at that level, there's enough buffering already in the plant roots, possibly from calcium in the cell walls or something that's going on that's not causing that shock to take place. But I think a prolonged exposure to a low pH would probably denature your proteins that make the roots not function.
Yeah, but let's say it's brought down to 6.5.
Okay.
Still consider that as a shock?
No. It is a change to the community. The most powerful driving force for microbial community selection is pH. If you change the pH, we did this in an experiment. We looked at the community profiles of the bacteria and fungi in the plants, mostly the bacteria. And as you adjust the pH of the soil down, you see completely different communities shifting over. So it could have impacts that we're not aware of yet. There's a lot of, my interest is in microbiology, and I work a lot with plant growth promoting bacteria. And I would like to have conditions that we maintain that keeps high population levels of those plant growth promoters. And how that's affecting these populations, I don't know. But it's a very open question.
But if you stayed at no less than 6.5 in your water,
Yeah.
you wouldn't be looking for a big problem.
No, because the plant growth promoting bacteria are actually, they prefer a pH close to neutrality, around 6. Yeah. As you go down, you shift over to bacillus and other types. But your plant growth promoters are primarily their alpha proteobacteria, and they like this pH 6, 7, so they'd be fine with that. Yeah.
Are there any ways to promote the optimal plant growth promoters other than optimal pH?
Yes.
Can you apply? Are there effective ways to apply these?
We've got a published study looking at the effects of salinity on different rootstocks on plant growth promoting bacteria. And one of the biggest groups, this is really turning into solid science. A lot of it was initially pioneered kind of in soft science, but there are bacteria that produce an enzyme that suppresses the production of ethylene. And ethylene is this plant stress hormone. When it builds up to high levels, the roots will stop growing. And that's what happens under hypoxia. They release high amounts of ethylene, and then that causes roots to stop, and it also affects the entire plant physiology. These bacteria that are on the surface are able to take this precursor of ethylene and degrade it and suppress the ethylene production, and then the plants can grow through that stress. And there's dozens of studies in the literature showing that they can improve tolerance to heavy metals, salinity, drought, temperature, chemical stresses. So the level that you want to maintain is about 100,000 per gram of soil. And then actually how you maintain those, you need a near neutral pH, and these bacteria like high amounts of soluble organic carbon, which means compost or actively degrading organic matter. So if you're maintaining a mulch layer at near neutral pH, you are already promoting a healthy environment in terms of the microflora, the microbiome associated with your plant roots. And that's coming from different sources, but we're applying the same neural network tools to that type of study as well, where we can see these population shifts in response to different soil conditions, dissolved organic carbon, pH being primary.
So it's not necessary, or maybe it's not even effective to actually apply the microorganisms.
Yeah, the question is it effective to apply microorganisms? If you can afford to apply them, it does improve things, but it's totally impractical on an avocado or an orchard production system. We produce them in the lab. We have, it takes about $10 to prepare a great big flask, for the chemicals. You pour it on the soil and it's done. You couldn't do this on a scale that would work at an orchard. It would cost you millions of dollars to bring them up to that level. So there are inoculants out there. We know bacteria work. But actually applying them, their survival in the soil, there's many, many studies that show that they decline often by 99% within a week. They simply fill up the macropores, the amoeba and the nematodes come along. It's like a buffet for them. And there's no survival of these bacteria in the soil over time. The only way you can do it was the approach that John Mingy was using with the inundative, every week applying 1 billion bacteria per milliliter to the orchard, and then you could bring them up artificially. But in terms of soil inoculants, this is one of my main areas. We've been trying to develop ways to do this. We're going off topic here, but one of the ways that we're looking at is using biochar, which has all this matrix of pores. You can load that with the bacteria, and it provides a protected habitat that improves their survival. So there's still some development in technology, inoculation technology, that might be able to deliver these bacteria to the field, superior strains and so on. But we're not there yet. Well, let's look one more case here on this neural network and the effects on fruit quality. And this should be very interesting to index, because what we're looking at now are things that they can market. And we know that many of the health benefits in avocado fruits are associated with the 7 carbon sugars, berceatol and manoheptulose, and even patents out there now to use these in food additions and food supplements, and even in toothpaste as anti-cancer compounds and anti-insulin compounds, preventing glucose metabolism. Very interesting materials. But we look at the fruit phosphorus content, and this is derived from the model. As you bring in increased levels of phosphorus into the fruit, we see the levels of perseitol and manoheptulose increasing. So having high levels of phosphorus is not only going to improve the tree nutrition in general, it's going to make a better quality and more healthy fruit. In our work, we also did a sensitivity analysis, and this is an output from the Synapse program, and it identifies factors that are associated with the time to ripen. So in this case, Mary Lou Arpaia has had fruit that she's collected. They put it into cold storage for 3 weeks. Then they take it out and they measure the length of time it takes for it to ripen. It gets to the point where they can squeeze it and it's ripened. And what we see is that phosphorus is very important here as well. Chloride is one of the main drivers, and we already know from the literature that calcium is important, but chloride is one of the main factors identified in this model. So now we look at the effects on time to ripening on leaf calcium. This is not fruit calcium, but leaf calcium levels and leaf chloride levels. Now, under low leaf calcium levels, 1.2%, and high chloride, you can see that as soon as you take that out, that fruit out of the storage, it's already ripe. It has 0 ripening time. That's not a good thing, because what this means is that after you take it out of storage, you've got to get it into the marketplace. It's got to go on the shelf. The consumer has to buy it, take it home, look at it for a couple of days, and figure out when they're going to eat it. And already this fruit is ripe if it comes in with high chloride, 0.9% in the leaf, and low calcium. If you have high calcium, this is associated with a storage time of 6 days. And on the other hand, if you maintain low leaf chloride down here at 0.1%, and you have high calcium levels, you can get up here to a 10-day storage time or shelf life time after it comes out of storage. So it's directly impacting the amount of time that you have to market your fruit. And I was learning yesterday in South Africa that they're looking at nitrogen ratios, nitrogen and calcium ratios in the fruit as a fruit quality standard. And if it doesn't meet certain criteria, the packing houses cannot export it, they can't use it, they won't accept the fruit. So I think looking at these types of relationships really have some value in terms of fruit quality protection and assessment by the packing houses as well. So we're getting lots and lots of really interesting relationships that are coming out of the models. I can show you some others at future reports. You can find this information in the latest report that's online now with the California Avocado Commission. And if there's particular questions, we're already discussing some of this, that if there's particular questions that we need to look at, I'm open. We have these models. We run independent models for different variable combinations. There's a procedure we go through where we run about 10 different models and look to see if it's a consistent result. We optimize the training. Once we have it, we can begin to examine any relationship that you're interested in and determine with a confidence interval what factors are affecting the production or alternate bearing or whatever it is. And right now we're doing this with Carol Lovett's got a large data set spanning several years. We're looking at those relationships, and then we're moving into the rest of our data that's coming from this large field trial. And I think we're going to have all kinds of really great information for you in the next year or so. Current status is that we have a very firm proof of concept that the artificial neural network models are correctly identifying well-established relationships. Our models are showing the benefits of maintaining a low soil pH, calcium additions. This would be best accommodated through use of gypsum, but it can also be facilitated by lowering the pH of a high pH soil above 7. And is suggesting increased requirements for phosphorus. And so overall, based on the fact that it's able to see these patterns very quickly, I think the artificial intelligence is working. For you, what I would recommend, know your soils. Go to that web soil survey. That is a free site. It will give you a wealth of information. Whether you're designing a new irrigation block or you want to see, am I passing sand over clay or what's happening here, it gives you the complete soil profile, what you've got, your soil texture and clay content, hydraulic conductivity, tremendous source. Use Tzimmes. This will establish your basic water budget, and you can do a lot better scheduling if you're following your ET measurements. Maintain a water budget. You should be hitting 4 acre-feet with your water. If you're applying 6 or 7, you're wasting water and probably causing chloride damage. Use soil water monitoring equipment. Even though this is fairly expensive, if you get it installed in the right place, in the right block that represents your irrigation block, it's an extremely valuable tool that can guide when to turn on and turn off your water. And recommending, in this case, gypsum block in the root zone, and then watering until your volumetric water content, set that where you want the water to perch before it finishes draining. So you can even have it at a lower level, and there are tubes that will measure the volumetric water content at different depths. But once you turn that water off, it'll continue flowing. And ideally, at the end of the irrigation, you want to end up with water in the root zone, and maybe just a little beyond for leaching. But if you are pushing it down here and your roots are here, that's lost money. So use your water monitoring equipment. It'll cost you a couple $100 for each setup, but potentially could save you $1,000 your first year if you're saving an acre-foot of water. Avoid hypoxia, especially in leaching, and I think we have to develop better leaching programs. There's some really interesting information I've come across on leaching. Often the recommendations are too high. Lao Sheng Wu, as a hydrologist in our department, along with John Letty, revised leaching recommendations that were made early by the Salinity Lab and say we're applying too much water. And also pulse irrigation. The most effective irrigation is actually, or leaching is actually a slow rainfall or slow application of water that allows the salts to come out of the micropores and push down. If you do a heavy immediate irrigation leaching, it's not very effective. I was reading back in 1962 in Tule Lake, they had this saline soil, and they applied 6 acre-feet of water to leach it. And they found that they only brought the salts down by half, and that half that they brought down occurred with the first half-foot of water. All that other water they applied was wasted. And it's only by a slow infiltration that the micropores are able to empty and go into the macropores and then push down and drain. So I think there's a lot we can do with customizing in our leaching programs. Lowering your pH, I recommend elemental sulfur. If you're not comfortable with sulfuric acid, it is a hazard potential, but it is the cheapest way to do it. It's effective, but potentially dangerous. Sulfur burners, these are becoming very popular. A little more labor intensive, a little more expensive than sulfuric acid, but much less than, say, N-furic, and relatively quick. If you're using N-furic, you can use it to supply nitrogen, but I would not use it to supply acidity. So those would be specifics. And in future directions, I think there's some really interesting things going on with this computer automated scheduling. I think this is the only way that we could do these pulsed irrigation, because it requires turning water on and off maybe 15 minutes, an hour, 15 minutes, this sort of thing, in order to get the effective leaching. But with computer automated scheduling, we have that. And we can also have flow volumes, actual quantities of water applied. You can do leak detection. I think this is a really powerful direction for water savings and maintaining viability of avocado here in California. Precision fertilization, I think this is going to be coming into play too. And then lastly, this year we're seeing the advent of unmanned aerial vehicles, drones, the use of multispectral cameras and thermal imaging to look at variation in the orchard. And this is my last slide, but I put it in as an important future direction because in many cases, I still don't think you can put enough soil probes in, and what we need to look at are the trees themselves. And there's a lot in the literature in just the last 2 or 3 years that is showing the utility of these techniques. A flyover with a multispectral camera, a thermal camera, if the plant's not transpiring, the canopy heats up. You see a signal. That tells you that it's either under or overwatered. You can look at insect infestation, salinity damage, nutrient levels in the leaves, especially nitrogen. Tremendous possibilities. And so you find hot spots and you say, okay, what's going on here? And I think having this direct feedback between the spectral images of the orchards along with your soil maps and overlays, that it will really help to guide precision management of our orchards much better.
In this county, Ventura County, and some of our soils plant on very heavy soil. Your thoughts on whether leaching actually leaches anything in heavy soil? Because and then I've also seen people who try to leach actually wind up with hypoxia because of the soil type and the fact that it doesn't leach. It's heavy. It's a clay.
Yeah.
And you have any thoughts on that?
If you have heavy soils, it's going to be a challenge all the time. Whether the first question was about is leaching effective or useful in these soils? You have to get rid of that salt some way or another. If you only applied water in the root zone, after even one season without leaching, you would be over the top in salinity. And there's no way you could grow trees very long doing that. So we have to have leaching, but how you do that needs to be customized. And one of the things that you're looking at is trying to maintain the macropores for airflow into the soil. So you either want to bring the soils up with mulching, that's the first thing. You want to have a good rootstock. If you have a choice in that, that's your very first selection. And there's a lot of exciting new work going on with these rootstocks. But if you're dealing with a heavy clay soil, the other part would be maybe you need to change the irrigation water application rate so that you're allowing the soil to drain and those macropores to open up and introduce oxygen again. So you might have to change out your emitters or optimize your scheduling and flow rates in order to get the soils to be well aerated. And I think the use of pulse irrigation, if it's done correctly, could be more effective. Pulse irrigation was developed 50 years ago, and Steve Cockerham used it on the most expensive turf in the world. And he was able to show that even with a regular water application, you could pretty much obtain effective leaching if you do it right. But in order to do that, you're turning valves on and off every hour, and that's not practical unless you have a computer-operated system. But certainly would be the best way to leach.
Because of the Philophicus shot hole borer, we've been told not to move mulch from anywhere to our property. Is there anything in place of that you can use in place of using mulch?
Well, it's a real concern. The questions about the Polyphagus shot hole borer, and if you import wood from other areas, wood chips, you could be importing the insect into your grove. And it's a very real concern. Especially now, as we know so little about the insect, I think we have to have extraordinary caution. There are treatment methods that are already being developed. For example, Ruben Hofschi's talking about using phosgene gas, that you can tarp your materials and put in phosgene. In 3 days, it's gone. It's used for killing termites, but at low levels, it also is effective against these shot hole borers. So there might be a way to do that, and then you could transport wood and mulches and so on. So I think in the future, as we understand more, that this will alleviate a little bit. But for now, they're right. You should only be using your own wood chippings from trees that you know are not infected. And honestly, I would even be careful with the traps. Where we don't know yet whether they're lures or traps. And so this is another concern. Yeah, you're getting into some interesting topics there. All right, well, thank you very much.
All right, well, thank you very much, Dave, for that discussion on the relation between water, soil, and fertilizer and avocados. Just as a quick summary, Dave talked about measuring water quality, and there's various ways to do that, whether TDS, electroconductivity, chloride, or sodium. That it's important to measure water availability in different types of soil, sand, silt, and clay. It's important to understand what we do when we irrigate in terms of flushing salts, increasing the water potential, and increasing soil saturation. Tzimmes is an important tool to measure and forecast water needs for avocados. An important point that he wanted to emphasize was overwatering can increase chloride uptake. And then he summarized in talking about the artificial neuron network and trying to model what will happen in avocado production as various aspects of the farming, whether it's soil, water, fertilizer, change during the season.